Polar coordinates. The coordinate system we are most familiar with is called the Cartesian coordinate system, a rectangular plane divided into 4 quadrants by horizontal and vertical axes. In earlier chapters, we often found the Cartesian coordinates of a point on a circle at a given angle from the positive horizontal axis. Sometimes that angle, along with the point's distance from the origin, provides a more useful way of describing the point's location than conventional Cartesian coordinates. Polar coordinates. Polar coordinates of a point consist of an ordered pair, r, theta, where r is the distance from the point to the origin, and theta is the angle measured in standard position. Notice that if we were to grid the plane for polar coordinates, it would look like the graph to the right, with circles and incremental radii and rays drawn at incremental angles. Example 1. Plot the polar point 3, 5 pi divided by 6. This point will be a distance of 3 from the origin at an angle of 5 pi divided by 6. Plotting this. Example 2. Plot the polar point -2 pi divided by 4. Typically, we use positive r values, but occasionally we run into cases where r is negative. On a regular number line, we measure positive values to the right and negative values to the left. We will plot this point similarly. To start, we rotate to an angle of pi fourths. Moving this direction into the first quadrant would be positive r values. For negative r values, we move the opposite direction into the third quadrant. Plotting. Note the resulting point is the same as the polar point, 2, 5 pi over 4. In fact, any Cartesian point can be represented by an infinite number of different polar coordinates by adding or subtracting full rotations to these points. For example, same point could also be represented as 13 pi divided by 4. Converting points. To convert between polar coordinates and Cartesian coordinates, we recall the relationships we developed back in chapter 5. Converting between polar and Cartesian coordinates. To convert between polar r, theta, and Cartesian xy coordinates, we use the relationships cosine of theta equals x divided by r, x equals r cosine of theta, sine of theta equals y divided by r, y equals r sine of theta, tangent of theta equals y divided by x squared plus y squared equals r squared. From these relationships and our knowledge of the unit circle, if r equals 1 and theta equals pi thirds, the polar coordinates would be r theta equals 1 pi thirds. And the corresponding Cartesian coordinates xy equal half square root of 3 divided by 2. Remembering your unit circle values will come in very handy as you convert between Cartesian and polar coordinates. Example 3. Find the Cartesian coordinates of a point with polar coordinates r theta if 5, 2 pi divided by 3. To find the x and y coordinates of the point, x equals r cosine of theta equals 5 cosine of 2 pi divided by 3 equals 5 multiplied by negative halves equals negative 5 halves. Y equals r sine of theta equals 5 sine of 2 pi divided by 3 equals 5 multiplied by square root of 3 divided by 2 equals 5 multiplied by square root of 3 divided by 2. The Cartesian coordinates are negative 5 halves and 5 square root of 3 divided by 2. Example 4. Find the polar coordinates of the point with Cartesian coordinates -3, -4. We begin by finding the distance r using the Pythagorean relationship x squared plus y squared equals r squared. -3 squared plus -4 squared equals r squared. R equals 5. Now that we know the radius, we can find the angle using any of the 3 trig relationships. Keep in mind that any of the relationships will produce 2 solutions on the circle, and we need to consider the quadrant to determine which solution to accept. Using the cosine, for example, cosine of theta equals x divided by r equals -3 fifths. Theta equals 2 pi minus 2.214 equals 4.069. Since the point -3, 4 is located in the third quadrant, we can determine the second angle is the one we need. The polar coordinates of this point are r, theta equals 5, and 5.069. Polar equations. Just as Cartesian equation like y equals x squared describes a relationship between x and y values, on a Cartesian grid, a polar equation can be written describing a relationship between r and theta values on the polar grid. Example 5. Sketch a graph of the polar equation r equals theta. The equation r equals theta describes all of the points for which the radius r is equal to the angle. To visualize this relationship, we can create a table of values. We can plot these points on the plane and then sketch a curve that fits the points. The resulting graph is a spiral. Notice that the resulting graph cannot be the result of a function of the form y equals f of x, as it does not pass the vertical line test, even though it resulted from a function giving r in terms of theta. Although it is nice to see polar equations on polar grids, it is more common for polar graphs to be graphed on the Cartesian coordinate system, and so the remainder of the polar equations will be graphed accordingly. The spiral graph above on a Cartesian grid is shown here. Example 6. Sketch a graph of the polar equation r equals 3. Recall that when a variable does not show up in the equation, it is saying that it does not matter what value that variable has. The output for the equation will remain the same. For example, the Cartesian equation y equals 3 describes all the points where y equals 3, no matter what the x values are, producing a horizontal line. Likewise, this polar equation is describing all the points at a distance of 3 from the origin, no matter what the angle is, producing the graph of a circle. The normal settings on graphing calculators and software graph on the Cartesian coordinate system, with y being a function of x, where the graphing utility asks for f of x or simply y equals. To graph polar equations, you may need to change the mode of your calculator to polar. You will know you have been successful in changing the mode if you now have r as a function of theta, where the graphing utility asks for r of theta or simply r equals. Example 7. Sketch a graph of the polar equation r equals 4 cosine of theta and find an interval on which it completes one cycle. While we could again create a table, plot the corresponding points, and connect the dots, we can also turn to technology to directly graph it. Using technology, we produce the graph shown here, a circle passing through the origin. Since this graph appears to close a loop and repeat itself, we might ask what interval of theta values yields the entire graph. At theta equals 0, r equals 4 cosine of 0 equals 4, yielding the point 4, 0. We want the next theta value when the graph returns to the point 4, 0. Solving for when x equals 4 is equivalent to solving r cosine of theta equals 4. R cosine of theta equals 4. Substituting the equation for r gives 4 cosine of theta multiplied by cosine of theta equals 4. Dividing by 4 and simplifying, cosine squared of theta equals 1. This has solutions when cosine of theta equals 1 or cosine of theta equals negative 1. Solving these gives solutions theta equals 0 or theta equals pi. This shows us at 0 radians we are at the point 0.4, and again at pi radians we are at the point 0.4, having finished one complete revolution. The interval 0 less than or equal to theta less than pi yields one complete iteration of the circle. The last few examples have all been circles. Next, we will consider two other named polar equations, a Limason and Roses. Sketch a graph of the polar equation r equals 4 sine of theta plus 2, what interval of theta values corresponds to the inner loop. This type of graph is called a Limason. Using technology, we can draw the graph. The inner loop begins and ends at the origin where r equals 0. We can solve for theta values for which r equals 0. 0 equals 4 sine of theta plus 2. Negative 2 equals 4 sine of theta. Sine of theta equals negative half. Theta equals 7 pi divided by 6, or theta equals 11 pi divided by 6. This tells us that r equals 0, so the graph passes through the origin twice on the interval 0 and 2 pi. The inner loop arises from the interval 7 pi divided by 6 less than or equal to theta less than or equal to 11 pi divided by 6. This corresponds to where the function r equals 4 sine of theta plus 2 takes on negative values, as we could see if we graph the function in the plane r theta. Example 9. Sketch a graph of the polar equation r equals cosine of 3 theta. What interval of theta values describes one small loop of the graph? This type of graph is called a 3-leaf rose. We can use technology to produce a graph. The interval 0 pi yields one cycle of this function. As with the last problem, we can note that there is an interval on which one loop of this graph begins and ends at the origin, where r equals 0, solving for theta. 0 equals cosine of 3 theta, 0 equals cosine of u equals pi divided by 2, or u equals 3 pi divided by 2, or u equals 5 pi divided by 2. Undo the substitution. There are 3 solutions on 0 less than or equal to theta less than pi, which correspond to the 3 times the graph returns to the origin. But the first 2 solutions we saw for above are enough to conclude that one loop corresponds to the interval pi divided by 6 less than or equal to theta less than pi divided by 2.